Friends, last time we already discussed the what is meant by even elimination, E2 and even CB. So today we are going to discuss in detail the E2 elimination reaction. So first we think about what is a general example of E2 elimination. So we consider the 2-bromopropane here. And when these 2-bromopropane we treated in a strong base like sodium methoxide, and when what happened in this case, there are this is a beta hydrogen, this is a beta hydrogen, and in this case there is a formation of a product, this one, and then there is formation of NaBr plus MeOH. So this is a simple or general example of E2 elimination reactions. We take a 2-bromopropane, they are treated with a strong base like a sodium methoxide, formation of alkene, NaBr and the MeOH. So what is the kinetics of this reaction? And the kinetic study of this reaction shows that the rate of the reaction is directly proportional to the substrate as well as the base. So what happened in this case, the rate, or we say the rate of the reaction is directly proportional to the concentration of the substrate 2-bromopropane as well as the base sodium methoxide. So this is called the bimolecular reaction. And why E2 we call the bimolecular reaction? Because rate is directly proportional to the concentration of the substrate or the 2-bromopropane and the sodium methoxide as a base, and therefore we write rate is equal to K, then the concentration of the substrate and the concentration of base. And so this E2 elimination is the bimolecular second order kinetics, because the rate of reaction is directly proportional to the substrate as well as the base. Once we see the kinetics, then we see the mechanism of this reaction. And for that mechanism, we also take the general example, like you take this R dash, you take a CH2 and we take a leaving group is X. Here we use a base is a sodium methoxide, and when we use the sodium methoxide as a base, then what happen? This is the methoxide, it abstracts the proton, these electrons are given to here and they leave out the leaving group, and there is formation of a transition state. So we know this is your base is abstract the hydrogen, there is formation of bond between the base and hydrogen. Similarly, the bond between this beta carbon and hydrogen is break, and we know the bond between this alpha carbon and leaving group is break. So this is alpha carbon, this is beta carbon, and such a type of transition state formation takes place. And similarly, there is a formation of pi bond between the alpha carbon and the beta carbon. So we get this is a transition state. This is the first step and it is a slow step, or we call the rate determining step. And once there is formation of transition state, this is easily converted or cleave into the product, and we write this is your product. So this is a simple mechanism of the E2 elimination reaction. So what happened here? Your base is abstract the proton, then this bonded electron between carbon and hydrogen they are given to here, and there is a bond between alpha carbon and leaving group is break. So in this case what happened? There is a breaking of two sigma bonds, means the bond between the beta carbon and hydrogen is break, the bond between alpha carbon and leaving group is break, and there is formation of a pi bond between the alpha carbon and the beta carbon. So we remember where these energies comes to break the bond between alpha carbon and hydrogen, or either the bond between alpha carbon and leaving group and beta carbon and hydrogen. So here we see what happens when the base is abstract the proton, then the bond between the base and hydrogen is formed, and when the bond between base and hydrogen is formed, then we know when the bond formation takes place, the energy is given out, and this energy is used to break the bond between beta carbon and hydrogen. And simultaneously, the bond between alpha carbon and beta carbon, there is a pi bond formation takes place. Then again energy is given out, and this energy is used to break a bond between alpha carbon and the leaving group. So in such case, the bond breaking and bond formation takes place in E2 elimination. And once all the bond formation and bond breaking takes place, because we see in first step it is slow step, the bond between base and hydrogen is formed, bond between beta carbon and hydrogen is break, the bond between alpha and beta carbon formation takes place, that is a pi bond, and the bond between alpha carbon and leaving group is break simultaneously. Means in E2 the bond formation and bond breaking takes place simultaneously, or it is a concerted process, and it is single step. Single step is a rate determining step. There is formation of transition state, and transition state easily converted into the product. So this is the simple mechanism of this reaction. Then what happened here, we remember, once we see the mechanism, we see the general example, then we see the kinetics of this reaction, then what is the evidences for this mechanism? Means we know, we call this is the alpha carbon, this is the beta carbon. And what happened in case of E2? It is a concerted process. Bond between beta carbon and hydrogen is break in a slow step or rate determining step. So we provide a proof for that. Again, the bond between the alpha carbon and leaving group is also break in a slow step. So that's why we also provide the proof for that, means how the bond between alpha carbon and leaving group is break in a slow step. And then we say that this is a E2 elimination mechanism. So there are some evidences for E2 mechanism, and there are the three evidences is there. And the first evidence or three evidences, the first one, kinetic isotopic effect. This is a kinetic isotopic effect. This is the first proof. Means we want to prove the mechanism of E2 elimination. Just now we already discussed. Then we have to prove the kinetic isotopic effect. So this is the first evidence for the mechanism of the E2 elimination. What is meant by the kinetic isotopic effect? In any reaction, any atom, or we change any atom with its isotope, and then when the rate of reaction is changed, then this process is called as a kinetic isotopic effect. So means what? We take one simple example, and then we think about this kinetic isotopic effect. Where you take this is simple example, and what happened here? We use here the sodium ethoxide as a base. Mechanism takes place by the E2, suppose. And then what happened? What is the rate of that reactions? We call the KH. Means what? This is the ethoxide base, attack on hydrogen, then these electrons are given to here, the leaving group is leave out, and formation of a product. This is the product. What happened in case of the first reaction? We take a hydrogen. You take in second reaction, instead of hydrogen, we take a deuterium. So that's why we take, instead of hydrogens, you take a deuterium, CD2, then we write Br. Then again, or instead of that, only we replace the beta hydrogen. We remember this is alpha carbon, this is the beta carbon. So what happened? We know this is alpha, this is the beta. And then instead of that beta hydrogen, we replace the hydrogen by its isotope, that is a deuterium. And then all the reaction conditions are same. Means instead of hydrogens, we write only the deuterium, but all the reaction conditions are same. The base is same and all things are same. So here we use sodium methoxide as a base, and then rate of that reactions we called Kd. Then what happened here? Then again we get the product pH CD double bond CH2. So such a type of products we get. And when we get this type of product, then what happened? Then we observe the relative rate or the rate of both the reaction. Then we observe that KH divided by KD is equal to 7, approximately 7. Means what? Means what? What is the meaning of that? The first reaction is 7 times faster than the second reaction, B reaction. So what happened here? What is important? Why the first type of reaction is a 7 times faster than the second reaction? Because we remember, in case of the first compound or first reaction, this substrate having the hydrogen. In case of the first reactant or first reaction, at beta carbon there is a hydrogen is there, but in case of the second reaction or second reaction B, at beta carbon there is a deuterium is there. And that's why means the rate of breaking of beta carbon and hydrogen is 7 times faster than the rate of breaking the bond between carbon and the deuterium. So we remember here deuterium is heavy than the hydrogen. So the energy is required to break the bond between carbon and deuterium is more as compared to the break the bond between carbon and the hydrogen. Means what? What is the meaning of these two reactions? Why the first reaction is 7 times faster than the second one? Because we remember in first case there is a hydrogen. Hydrogen require less. We want to break a bond between beta carbon and hydrogen. Then it require less energy. But in second case, what happened? There is a bond between carbon and deuterium. Because deuterium is an isotope of hydrogen. It is heavy and it require more energy to break the bond between carbon and deuterium. And that's why the first reaction is 7 times faster than the second one. But we remember this ratio or relative rate Ks divided by Kd is equal to 7 means what? The bond between the beta carbon and hydrogen and the bond between beta carbon and the deuterium is break in a slow step or rate determining step. Suppose the bond between beta carbon and hydrogen or beta carbon and deuterium is not break in a slow step, then what happen? The rate of both the reaction is the same. But what is the actual relative rate of the reaction? Kh divided by Kd is equal to 7. It indicates that in E2 elimination, bond between the beta carbon and hydrogen which is break in a slow step or rate determining step. Suppose the bond between beta carbon and hydrogen is not break in a slow step or in a fast step, then both the reactions having the same rate. But what is your observation? The first reaction is 7 times faster than the second one. It indicates that the bond between beta carbon and hydrogen in the E2 elimination is break in a slow step. Means E2 elimination shows a kinetic isotopic effect and reaction shows the kinetic isotopic effect. It indicates the bond between beta carbon and hydrogen which is break in a slow step in a E2 mechanism. Just now in mechanism we already discussed the bond between beta carbon and hydrogen is break in a slow step. So that's why the E2 elimination shows the kinetic isotopic effect. So this is the first evidence. Then the second evidence is there, and this second evidence is there. It is called the elemental effect. The elemental effect or elemental effect or the living group effect. And suppose here we take one general example. We take this one. Here we take a simple example. Here we take a base then E2 elimination, we form, this is a product, and we change a leaving group. In this case we take this substrate, but here we change only the leaving group, and then what is we take a different leaving group and we see what is the rate of E2. So we take the first one, we take a fluorine, then you take a chlorine, then you take a bromine, and lastly we take a iodine, and we see what is the rate of E2 elimination. When we see the rate of E2 elimination, then first reaction having the rate 1, second having the rate 10, then 4 into 10 raised to 3, and last one 2.5 into 10 raised to 4. So what is the meaning of this? What is the meaning of this? Why the rate is changed? By changing the leaving group, or it is called the elemental effect. Means in E2 elimination, when we change a leaving group, we take a fluorine, E2 rate is 1. You take a chlorine, it's 10. When you take a bromine, its rate is increased and it goes into the 4 into 10 raised to 3. When there is iodine, its rate is 2.5 into 10 raised to 4. So why the rate of reaction is increases when we change the leaving group? Means what is the effect of element or elemental effect? Means in E2 eliminations we change the leaving group, then the rate of reaction is changed. Means what is the meaning of this? Why the rate of reaction is changed? Because we already known the bond between this alpha carbon and leaving group is break in also in a slow step. When the bond between this alpha carbon and leaving group is not break in a slow step, or it is break in fast step, then you take a fluorine, chlorine, bromine and iodine. In all the cases the rate of reaction is same or it is constant. But we see that here you take a fluorine, it is not a good leaving group, rate is 1. Chlorine is good leaving group than fluorine, the rate is increased, it is 10. The bromine is good leaving group than the chlorine, rate is increased 4 into 10 raised to 3. And iodine is a good leaving group, so that's why its rate is again more 2.5 into 10 raised to 4. Means this E2 elimination shows the elemental effect. Means we change the leaving group, then the rate of reaction is changed. And why the rate of reaction is changed? Because the bond between the alpha carbon and leaving group is break in a slow step. When the bond between alpha carbon and leaving group is break in a slow step, then we change the leaving group, then the rate of reaction is changed. And we observe here the iodine is a good leaving group, it is depart easily from your substrate, so the rate is more. Then fluorine is a bad leaving group, so that's why the rate is 1. So it is not easily depart from your alpha carbon. So that's why we remember that when you take a good leaving group, rate is good or rate is more. When you take a bad leaving group, rate is less. It indicates that the bond between alpha carbon and leaving group is break in a slow step. Then you take a next point, the absence of hydrogen exchange. This is last evidence, and third one, the absence of hydrogen exchange. Absence of hydrogen exchange means in this case we want to differentiate your substrate follow the E1CB mechanism or your substrate follow the E2 mechanism. So that's why we see this is the hydrogen exchange experiment. And when we take a simple example, that is a 2-phenyl ethyl bromide. 2-phenyl ethyl bromide. We take this is your substrate, suppose. And what happened in this case? We take this substrate and this substrate we treat in a sodium ethoxide. And when this substrate we treat in a sodium ethoxide, so but this substrate follow the E2 mechanism or E1CB mechanism. So that's why suppose this is your first, in this case, we know, we take this type of example, and then what happens, suppose, when this substrate is reacts by E1CB, then we know there is a formation of carbanion in first step. This is carbanion. And what happened? This is the first step, A. What happened in B step? When you take this is your carbanion. This carbanion given the electron here, leaving group is leave out, and we get your product. Means suppose your reaction follow the even CB, then such type of product formation takes place. But we remember what happened. When you take this substrate, then you take a sodium ethoxide. When the 50% reaction is completed, then we add that is a deuterated ethanol. Means in C, this is the experiment, and in third step what happened? Suppose your reaction is complete, or your reaction is complete 50%, then in reaction mixture we add ETOD, deuterated ethanol. Means what is the sequence we remember? You take this substrate, we take a base. When suppose we see the even CP mechanism, then there is formation of carbanion. In second step of even CP, what happens? These electrons are given to here, leaving group is leave out to form the product. But in this experiment, suppose you take this is your substrate, then they are treated with the base, sodium ethoxide, then 50% carbanion formation takes place, then again in the reaction mixture, we add deuterated ethanol. And when we add a deuterated ethanol, then what happens? We get such type of product. We get this type of product and we write Br. So what happened here? We get hydrogen exchange product, and we remember recovery of the starting compounds, instead of hydrogens we get a deuterium. Means what is the meaning of that? What is the meaning of that? When these products we recover in your reaction mixture, then we say that your reaction mixture or your substrate follow the even CB mechanism but don't follow the E2 mechanism. Means we remember you take substrate, base, then formation of carbanion. Once the 50% carbanion formation takes place, then we add deuterated ethanol, and suppose this type of deuterated product formation takes place. This is your starting compound, and instead of hydrogen there is a deuterium. Such type of compounds we get into your reaction mixture, then you say that these substrate follow the even CV mechanism but don't follow the E2 mechanism. But in actually we take this type of substrate and we don't get this type of product. We don't get this type of product in your reaction mixture, so it indicates that this substrate, means we take a 2-phenyl ethyl bromide, is not reacts by even CB but it reacts by the E2. So that's why this is a simple experiment, and then absence of hydrogen exchange. Means in E2 elimination there is absence of hydrogen exchange. So when the reaction follow the E2 mechanism, then the hydrogen exchange product formation never takes place. And in actually when you take a 2-bromopropane is there, then such type of the hydrogen exchange product we never get in a reaction mixture, and it indicates that the this is a 2-phenyl ethyl bromide, it reacts by the E2 elimination but it don't reacts by the even CB mechanism.